Good afternoon, everyone. It depends on where you are. Um, I want to thank the organizers for giving me the opportunity to present part of my PhD thesis. My name is Scholastica Emenike from the University of Glasgow. This research is funded by the Petroleum Development Trust Fund. And the topic of this presentation is optimization of gas loss and CO2 emission during disruption of the natural gas network. It's a case study-based research, and raw data were collected from Nigeria. I'll go straight to the presentation for lack of time. So this is a presentation outline, introduction, the methodology, the results, and the conclusion. Basically, an introduction of how global energy demand and consumption looks from the graph. Data analyzed by BP 2019 that shows the continuous rise in renewables followed by natural gas as a primary energy growth. And as a result of that, natural gas, it's majorly an intermediary between conventional and renewable. To buttress this, you find out that IEA 2016 carried out a research, and a projection of 28-year period shows about 48% increase in the demand for energy over this 28-year period. So as energy continues to grow, it's assumed that natural gas demand and consumption would grow. Now, the challenge is when there is an emission. An example is shown here of a compressor station in Oregon where there is a disruption on the network, and then you find out that methane, which is the major composition of natural gas, is emitted into the environment. Now, the challenge is the potency of this methane. Research shows that it's about 20% more potent than CO2 greenhouse gas emission. So as much as we could reduce the methane emission on a gas network, it gives value to that particular supply chain. The aim basically is to optimize for gas loss and carbon emissions during disruption on the network node. I'd like to say here that the disruption we're talking about is unplanned disruption, which is exogenous, and oftentimes, because there are no plans put in place, it becomes difficult, to manage the emission of gas loss. The assumption here is that when there's an interference of the network, there's a shutdown in the network node, and losses of gas are also incurred during this shutdown. Is a case study based research, like I earlier said, and there's a disequilibrium between demand and supply. Now, the objectives is to investigate the impact of we're proposing a relief pipeline. This proposed relief pipeline that's going to be used to reroute gas from the main line to the cell line. We're going to investigate the impact and examine the response of the system to disruption and the effect of this mitigation strategy. This takes us to the next slide. This is an overview, a schematic overview of the gas network. So you have the upstream, the midstream, and the downstream. And the gas is gathered in the gas gathering plant and then moved to the midstream for the gas processing or refining, and then to the consumers. Now, when there is a disruption between the upstream and the midstream, especially when it comes to the compressor station, because of the pressure from the upstream, there's a blowdown in the compressor station, and then the gas is emitted. So can we introduce a relief pipeline, an alternative pathway between the inlet and the outlet node, so that's to contain this gas and reduce the quantity of emission to the environment? So obviously the gas network, as we see, is interconnected and is complex, and these disruptions rarely occur, but when they occur, the economic, social, and environmental impact is usually significant. So the methodology is to develop a mathematical algorithm, mixed integer linear programming, and run it on gas network using simplex solver, and to allocate the appropriate pressure at the mass flow rate at critical nodes. And then we're going to be looking at different scenarios and comparing the result from the different scenarios. Now, looking at the binary variable, well, this first one shows us that the plant, the minimum online time, how much time is it expected that the plant will operate after its startup? And then the shutdown, we want to ensure that the minimum, the continuous shutdown time is less than the minimum online time. So we're introducing this topology redundancy, which is the relief pipeline as a mitigation effect. The underlying concept is to satisfy the mitigation effect of the disruption using this relief pipeline. And so you have the inlet and the outlet valves short, and then the introduction of this relief pipeline to reroute the gas from the main line to the seal line, so that there's a continuous flow, and then there is a reduction in the loss during the shutdown. So first of all, we had to look at analyzing at the baseline when the plant, there's a startup in the compressor. We analyze the performance of the compressor, and this is done by multiplying the mass flow rate by the operating time of the compressor. You find out that the compressor, there are 4 compressors in the compressor station. Now the performance is more steady towards the tail end, looking at the first graph. And then the second one, when there is a startup and the relief pipeline has been introduced, we optimize that by also multiplying the mass flow rate by the operating time. You'll find out that K1, which was very flat in the first graph, is showing a better performance. You know, even though they did not reach the optimum value, but the performance of K1 and K2 had increased at this point significantly. So the impact of the relief pipeline on storage and flow rate. Now we're using this relief pipeline as a capacity of 1.3 to 1.5, means 30% to 50% of the main line. That's the capacity of the relief pipeline, and using that as a line parking temporary storage. You find out that what is this, how does this storage also affect the overall flow rate or the throughput. And at this point where it shows a drop, a significant drop, that's the impact of the disruption, and when the line parking cannot take much more gas for temporary storage. Now when this is analyzed using the compressor, the plant node, at steady state, equal capacity, you find out that the pressure at each node within the upper and the lower bound limits are actually introduced, and then we relaxed the disruption period. We got this output, which we analyzed subsequently, and then we decided to alter the capacity of the plant node by also bringing in the pressure at each node within the upper and the lower bound limits, and we got this output here. So significantly, the time period where there's a shutdown at T8, 19 and 27, there is also a huge impact, because at the shutdown time periods which were introduced, a significant drop in the flow rate. So a different scenario that was brought in again, or which we introduced, is we without a flow constraint, but this time around extended time series. So we had to separate the normal time period, extended time period, and then have a cumulative time period to understudy the flow rate without a flow constraint. And then we decided to introduce a flow constraint in the same time series, where we had to separate extended from normal and then the cumulative. The result of these graphs is summarized in the subsequent slide. Remember, this is also a steady state, so expect that what goes in is what we expect to come out. So the performance, the first graph which we saw, where the capacity was flat, showed 327.67 mmF CFD. better than when the capacity we had varied capacity, even though the shutdown times were the same. And then when we had introduced the flow constraint, we had 336.08. But when the flow constraint was completely removed, we had a better optimized performance flow rate of the network. So the variation in shutdown here, as shown in this graph, we had to look at how does the mass flow rate affect the number of shutdown times and the optimum value. The table here shows explicitly that when we have a mass flow rate, a lower mass flow rate of 300/200 min max, the shutdown time is least, and the final solve is high, which is the optimum value is high. So the best mass flow rate at this point is 300/200 min max when the plant is operating, and when the plant is operating. So we had to do, based on the savings on the loss, using the baseline and the where we had the equal capacity of the compressor plant, and we realized that we had a significant savings on the shrinkage cost as a result of savings on the loss from 11,782.15. It came down to about 171.09. So let's look at the impact based on the potency of the methane. Now, we're using a conversion, isothermal temperature of 60 degrees Fahrenheit or 15 degrees centigrade. And we're using a conversion in kg, 8427210.92 kg per hour. And when we calculated this, we found out a net savings of 9,837.02 million kg per hour of CO2. And in tons, when we had to convert this in tons, we have 196,746 tons of CO2 equivalent savings. Alternatively, we use the FAST software, and it gave us a savings of 245.95 tons. And it shows us that there is actually a savings on CO2 as a result of this optimization. And so when we look at the total output performance, there is we find out that a reduced mass flow rate shows a reduction in loss and shortage and a higher throughput. And the best possible mass flow rate is a 300/200 for the main line. However, when the relief pipeline is equal to 1, when it's operating, we need a higher mass flow rate, as seen here. When you have 380/200, you have a higher optimum value. Now, the result also shows that the performance of an initial node affects the number of shutdown times in a steady state. In conclusion, the final solve has given us an integral optimal solution, and each node is constrained by the mass balance law. For all possible scenarios, there was no mass buildup in any of the node, and the best possible scenario is when we have the 300/200 psi as per pressure on the main line, and the best final solve gives us a 93.6% optimized solution. There's a target savings of 1.23% to 1.54% of CO2 equivalent based on the optimized solution. I just want to thank again my sponsors, the Petroleum Development Trust Fund, for sponsoring this research. I know there's no opportunity for questions, but I still want to say thank you for this opportunity once again. Thank you.